Good morning, ladies and gentlemen.
The distinguished chairman of 11th Joint Conference on Chemistry, Mr. Amin Fatoni, PhD.
And our distinguished professors, Professor Dr. Hassan Y. Abdul Imin from Egypt,
Associate Professor Dr. Yan Mulyana from Japan,
Assistant Professor Swarakron Linwood from Thailand,
Associate Professor Dr. Apun Muang from Thailand,
and also Mr. Roy Andreas, PhD from Indonesia. And thanks for participants for coming early this morning. Welcome to the second day of 11th Joint Conference on Chemistry.
List of agenda in second day would be first, second plenary session and coffee break.
The third parallel sessions.
The fourth, lunch break and Friday praying.
The fourth parallel sessions.
And the last is closing ceremony.
Now we are going to start the second plenary sessions. And we would like to invite Mr. Ismiarto, PhD, as moderator of second plenary sessions to come forward.
Mr. Ismiarto is lecturer in Chemistry Department, Faculty of Science and Mathematics di Ponorogo University, majoring Organic Chemistry Synthesis.
For the second plenary sessions, we'd like to invite three invited speakers. The first is Associate Professor Dr. Yan Mulyana from Japan. Please come forward. Second, Assistant Professor Swarakron Linwood from Thailand. Please come forward. And the third, Mr. Roy Andreas, PhD from Indonesia. Please come forward. These plenary sessions will be led by Mr. Ismiarto, PhD. Therefore, Mr. Ismiarto, the time is yours.
Ladies and gentlemen, good morning. In the second day of GCC 2016 in Purwokerto today, in the plenary session 2, we will enjoy the presentation presented by three speakers. The first speaker, Associate Professor Dr. Yan Mulyana, and I will introduce briefly curriculum vitae related to academic experience. Recently, from 2015 to present, he is as Associate Professor in Department of Applied Chemistry, Tokyo Metropolitan University, Japan, and related to research expertise, the interest to develop photo-induced water splitting, the synthesized solar cell, inorganic chemistry, molecular magnetism, and supramolecular chemistry. And the second speaker in this plenary session 2 is Associate Professor Waron Linwood from Thailand. And I will to introduce briefly about him. He worked at the Department of Applied Science, Faculty of Science, Branch of Sumba University, Hat Lai, and Thailand. And his major field of scientific specialization is analytical chemistry. And now he interests to develop about the research area in electrochemical analysis and chemical sensor and biosensor. And the third speaker in this plenary session 2 is Roy Andreas, PhD from Department of Chemistry, Faculty of Mathematics and Natural Sciences, Jenderal Sudirman University. And related to the academic preparation, he got the PhD degree in geochemical oceanography from University of Toyama, Japan, 2015. And now for the speaker, the first speaker in this case, Dr. Janaya Mulyana, to present your presentation. Please.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. This is a very amazing occasion for me to be able to stand up here in front of you, the audience. And I'd like to thank, first of all, the organizer, the committee for this conference, to invite me to come here and to give a little, to share the ideas, to share my research with you this morning. Before we begin, I'd like to just tell you about the focus of the title of my presentation is Materials, Medicine and Energy, about the versatility of the metal complexes. So my research is focused mainly on developing metal complexes. But before we start, I'd like to give you a little bit of my background. And I was born in West Java, actually. From my name, you'll probably understand that I come from West Java, I'm Sundanese. I studied in Unpad, so this is actually brings all my memory actually back to Indonesia last time. I'm thanking specifically this morning to Ibu Ika Wia, and he was taking some photographs. She's actually my supervisor in my undergraduate degree, so I'm thanking her for coming and watch my presentation. So 16 years ago, I moved to Melbourne, Australia. I moved to Australia, and I settled in Australia until now. So I come from that beautiful city of Melbourne. If you want to visit Melbourne, more than welcome. But from now, I work currently in Japan, in the University of Tokyo Metropolitan University as the associate professor in the Department of Applied Chemistry there. So the scope of my presentation is actually into three different areas, which are materials, medicine, and energy. And I'd like to explain why we can develop those focuses specifically for metal complexes, because my research is mainly focused on these metal complexes, which can be applied into materials, medicine, and energy. Right, because the organizer only gave me 30 minutes, so I have to really be strict with the time. So if you see this picture, I'm not sure what's going through your mind about this picture. But let's have a look at 1977, where this is the picture of, I don't know, who's that? It's Steve Jobs, that's right, the Apple founder. 1977, there's Apple II, and then 1989, they released the computer, which actually was able to, do the web browsing and things like that. And suddenly in 2007, we have smartphones, and after that, in 2010, we have the iPad, which is the, post-PC kind of gadget. And oh my God, this is very jadul as well. Sorry about the jadulism. It's actually an Indonesian slang for being old or something like that. As opposed to modernism, for example, something like this, you wouldn't probably imagine this still exists today, actually. Yeah? So, in summary, there's a miniaturization of the materials from big scale to the very, very small, tiny sort of materials for the application in small gadgets like that. So there's a process of being from bigger size to the smaller size. Okay, so that's why we need to understand there is a movement from the bulk material system into the molecular level. The computer system has the 10101 system, if you know that. And there's how can we get the molecular level or molecular size materials from this kind of category? So there's one term called Bistable Molecules, which displays two distinguishable states, and it can be interconverted between one state to the other. So some of the examples of that bistable molecules are single molecule magnets, spin crossover materials, and valence tautomeric materials. I'd like to explain a little bit more on these valence tautomeric materials as a molecular sized material. Right, let's have a look at the details, or just a little brief explanation about how it works. There's for example, there's a catechol and cobalt-3, there's a semiquinone and cobalt-2. These two can be interconverted. We can go from 3 to 2 to 3, depending on what kind of outside process that we have. So in principle, there's a redox active metal center, which is cobalt there, and redox active ligand around that cobalt center. Right, so I was focusing on this pretty simple metal complex there containing the little catechol with the very little ligands. I like to call it that particular compound. And when I crystallize it from pyridine and hexane, you can see there are two different molecules, 1 and 2, and this one is close to the pyridine and the other one it's not. So what's happening to that molecules when we increase the temperature of the crystallization? You can see here that everything is in cobalt-3 there, but this one, the one that is close to the pyridyl solvent stays at cobalt-3. The other one goes to cobalt-2. We can see that from the one length change actually, and also we can see that from the magnetic susceptibility data. We can have low spin to high spin at exactly about 250 Kelvin. And we can go back to that one again. So it's interconverted between cobalt-2 high spin and cobalt-3 low spin. And we can also trigger this process using the laser, 500 nanometer laser. We can go from cobalt-3 to cobalt-2 using laser. So we can conclude that that material is, I'm actually speaking really fast because of the time, sorry. So that material, in conclusion, is bistable, because we can go from 3 to 2 upon the application of temperature and light energy. So that the transition at about T-half at about 250 Kelvin, and the transition from this to that, and all from here to there can be also light induced at 9 Kelvin. So this is one of the examples of that bistable material that can be applied for the molecular size material. Now, we can now move to the second one, which is the medicine, right? So this is the second topic that I'd like to talk to you about. So why new medicines? I think everyone knows that the world has a very high demand of medicines because of the new diseases, especially in the tropical region, we have a lot of variety of these diseases. And one thing that we have to understand is the drug resistance, actually. So that we have to fight with the drug resistance. I'm sure Professor Hassan knows more about this than myself. Metal complexes medicine. How can we apply the metal complexes in medicine? This is the very well-known anti-cancer drug, which is still being used till today. It's the most effective one, actually. The cisplatin. But actually, the cisplatin has some problems, which is related to the drug resistance, side effects such as kidney damage, hearing loss, and things like that. It's been reported in this paper. So we need to find a new alternatives for replacing the cisplatin. Right. So I'd like to show you in the next slide. So this is what we have researched so far. The dinuclear metal complex, which has been reported in Coordinates in Chemistry Review. And my work was to expand the research into a lot of variety of complexes, ranging from dinuclear series to mononuclear series and to polynuclear series. For example, here I'm showing you trinuclear, and I'm showing you also the tetranuclear complexes, all having the variety of linkers, the alkyl chain, the one that has the amine moiety, and the one that has a polyether. We can make the mononuclear series, we can also make the dinuclear, and we can also make the polynuclear. So this is the one that I did after making or after synthesizing all those complexes. I studied the drug-DNA interaction. In principle, I'm using DAPI fluorescence replacement assay, and I'm also testing it against the single verge and the duplex DNA as well. And we can see here from the DAPI fluorescence assays, the one that is active is actually RAB7. I call it RAB7. That's the one that has the alkyl chain with the 7 length. And we can also see that RAB7 actually prefers to bind into the single verge DNA. So that's one of the research focus that I did last time. And we also did the cellular uptake where the cell that I studied was the leukemia cancer cell line. And we can see here, please pay attention on this table there. That's the cisplatin, which has one sort of activity, IC50 about 1. And if you see here, the number is really high, but that one, look at that, it's really, really active because it's really close to cisplatin. So this is really, really interesting point of view of, ruthenium complex as a very, very good alternatives for replacing the use of the cisplatin. And we also did some, cellular uptake and cellular accumulation of the metal complex in the mitochondria. And we luckily we published it in Chem Journal last time. This was regarded as the VIP paper last time because of the very high activity of those complexes. Okay, so that's about the medicine and what we call that, the materials. Now we are moving to the energy. This is actually the one that I'd like to speak most, because this is actually the recent research that I started doing in the Voltometry University in 2015, even before that when I was working at Monash University in Australia. All right, so how can we apply metal complexes into energy? Now, okay, I'd like to ask you the question, who is sure that in 50 years we're going to have this the car that runs by water? Who is sure? Just raise your hand. Or I only have 1 or 2, 3. Okay, all right. I am the one that is sure about it. In 50 years, we can get the car that runs by water. Right. So this is the current condition, right? We use petrol fuel for running the car. But it might be that in 50 years we can have this car. Just put it into water in it, the car's running. So this is the one that we have to do. Why? Because we're not going to get the petrol fuel in the future anyway. Maybe in 100 years it's going to be running out. So what are we going to do with it? We need to find out a new source of energy that is renewable. Right. Okay, but before we do that, we need to learn how to split water. That is the key. Right. We have a lesson. We have a lesson from nature. In the photosynthesis system, water can be split into oxygen, and the electron can be used to to drive the biochemical processes. So that's how the nature actually splits water, using sunlight energy, right? Now we can copy this. Imagine we have a bio-inspired energy materials where water input, photon energy, and we can get oxygen and hydrogen at the same time after that. So that's the very, specific technology that we need to develop in the future. So we can get hydrogen fuel from this system. Excuse me. So these are the experts on the field. Professor Daniel Nocera in Harvard is doing work on the metal oxide chemistry for the catalysis of water splitting. Tom Meyer in North Carolina, and also Lee Ching-Sun. These are the very famous experts on the field. And I'd like to show you just a little bit of joke on the next slide. Just don't be serious with the expert. Maybe the one who actually likes to split water is this guy here, Bruce Lee, actually. He doesn't drink water though, but he drinks water. So. Right. Okay, back to the serious business now. The nature of water splitting, why is it so difficult to split water? We need to understand why. Right, so let's have a look at the half reactions. That is the oxidation of water to oxygen, and this is the reduction of the proton to hydrogen. Right. This one is very easy, but that one is really difficult to understand. It takes about 1.23-fold at pH 0. Why? Because we need the term is called buffer potential. That is needed because we can see here there's a formation of stable diatomic oxygen-oxygen bond with the extractions of 4 protons and 4 electrons at the same time. So this is why water splitting is really difficult to understand. So that's why we need efficient catalysts to undertake that, to proceed with the process. Right. So this is the one that I have studied so far. I'm developing some ruthenium chemistry, which has a function to catalyze the oxidation of water. Right. In the homogeneous system, we can see there is the principle of why it can split water to oxygen. We can go from ruthenium 2 to ruthenium 3 and ruthenium 4 or 5 or 6. This is the one that is active to split water into oxygen. Right, but to go to that one needs an activator, and one that is mostly used for going from ruthenium 2 to higher oxidation state ruthenium is actually cerium-4. But we need to move on from the homogeneous system to the heterogeneous system for the application of the materials. That can be driven by light energy, and that's why we have to use an appropriate semiconductor for it to run. So we need to develop photoelectrochemical devices for that reason. So this is the one that I'd like to explain to you, just a little bit. In the photoelectrochemical PEC device, in principle there's a photoanode and there's a cathode. In the photoanode, there's a photosensitizer, I call it P, and in the photoanode as well, I call it, there's one side which is called VOC or WOC, which is water oxidation catalyst. So when that photosensitizer gets excited because of the application of the light, that excited state can give the electron to the conduction band of the titanium nanoparticle. Upon that process, the photosensitizer can oxidize the catalyst, nearby catalyst, from water to oxygen, produces proton. That proton travels through the membrane, goes to the cathode, and in the cathode, that proton is reduced to hydrogen, and you can use this as a fuel. So this is the principle of the PEC device, which is actually the one that copies the nature as well, the one that I showed you before. Right, this is the common design. There's also the alternative design that I actually developed in my laboratory using just the solution of the materials on the surface of the indium tin oxide particle. Right, so this is the one that I'm going to explain more on that in a few minutes. So this is the alternative design, which has the solution of the metal complex on that. I know this is boring. It has FTO, ITO nanoparticle as the working electrode, platinum cathode, silver chloride reference electrode, and ruthenium complex is dissolved in the electrolyte here. And this is the xenon lamp as a source of the light energy, and the electrode just as well as connected to the potential star. Right. I'm also studying for the first time the photoresponsive properties of the metal complex, for example, this one here, because it starts from chloro, I have to go to aqua. How I can get that? I can use the light energy to actually go from Cl to aqua. We can also monitor it with the UV visible spectroscopy as well as the NMR spectroscopy. So that's what's happening in the solution when we apply the light onto that sample. Right, so there's this is the complex solutions on the ITO surface. We can see the cyclic voltometry of those complexes. There's 2 redox waves within 2 to 3 and 3 to 4 here. So we can see that the water oxidation starts at pretty high applied potential, about 1.4. But the thing that I was interested in was what happened when there is a light applies to the IT particle. So we can see here the water oxidation started at 1.2 without any light, but after light application to that material, the water oxidation starts at lower potential, so which means we can do it using light energy. Right? But the question is, can water oxidation be photo-enhanced by the presence of metal complexes? The answer to that question is yes, because we can see from the photocurrent profile that the dinuclear complex, which I call it Cat5Cat, has the highest photocurrent value. You can see that in this diagram. And we can also see when we prolong that experiment for about 1 hour, the Cat5Cat is the best one. And not only that, indeed, the Cat5Cat produces hydrogen. The rest doesn't. So this is the very interesting finding for me. And I'd like to explain why Cat5Cat actually produces hydrogen and the other don't. So we can see from the SEM image, this is the SEM image before the photoelectrochemistry, and this is after the photoelectrochemistry of we can see in the Cat5Cat is evidence of the deposition of the complex on the nanoparticle, which is responsible for driving the water oxidation process. So there is accumulations of the high oxidation state of ruthenium complex on the IT or nanoparticle, right? And you can see from the CV here. Right, so when we see, unfortunately, there was no evidence of producing oxygen from that system. And I was kind of curious why. And we sort of predict that this 2-electron route, instead of going into oxygen, it goes to hydrogen peroxide. So that is the prediction. Because this is confirmed from the detection of the gas, of the hydrogen, but unfortunately oxygen was not detected, so we predicted that could be going into hydrogen peroxide. Right. So from this experiment I found some new concept that why is the dinuclear active and the other one it's not. So I had that question in my mind. So that it could be that in the dinuclear complex, the one side actually acts as the photosensitizer and the other one acts as the water oxidation catalyst, right? So that's my assumption. And it may be that there's intermolecular electron transfer from photosensitizer, or from the water oxidation catalyst to the photosensitizer. That's my assumption. So the new concept that I talk about is this one here, the bifunctional character, in which the material functions as both photosensitizing and catalyzing at the same time. Right. So I found some new concept, and this is really original. No one has reported it before. So I'm sort of competing with Daniel Monster at Harvard. I hope so. So the PEC design then, from this new concept, is the one with bifunctional materials. Instead of using P and WOC, I only use that material, this one material which functions, dual functions as the photosensitizer as well as the water oxidation catalyst. So I developed this kind of material. In the next slide I'm going to explain a little bit more on that one. The one that I was interested in is this complex, metal complex, ruthenium complex. Why I chose this? Because it has a good electron donating substituent that might lead into the effective electron injection. The high redox potential, it gives the powerful oxidizing character of the complex, and also the greater hydrophobicity because of this long alkyl chain that would give us the high stability in water. Now, because I have a new complex here, I have to compare it with the old one. This is the one that is currently used as the photosensitizer in the field of water splitting. Okay, I think I can skip this one, unless you want to ask that question later on. So the experimental setup, the deposition of the material in the titanium nanoparticle, I can get a colorful sort of material, and I set that up in the photoelectrochemical setup with the light source as well. This is the cyclic voltometry comparison between the RuBP, the old one, and the new one that I developed here. It's interesting because it's more powerful in terms of the oxidizing character than the old one, than the one that's currently used from the cyclic voltometry data. For example, the E-half value is more than the it's only 1.25 fold versus AgADCl, whereas the RuBP or the old one, it's only about 1.12. So, and also the IPC value is also higher than the old one, right? The one that we have to discuss is this thing, the linear sweep photometry upon the application of light. So we apply light on and off in this material. We can see the red one is the old one, the RuBP, and the blue one is the new one that I developed in the lab. So we can see here it has a much higher photocurrent than the old one. Right. So, and also surprisingly, when we did prolonged photoelectrochemical experiments, we can see here it's a huge difference between the new complex and the old complex. It goes to about 1 milliampere per centimeter squared photocurrent, whereas this one is only about 0.12, 0.24. The interesting thing is I could produce hydrogen from that system, which means that we do not need multi-component, we only need one or single component in that system. So I proved that this hydrogen, although it's a very small amount of hydrogen, it's only about 361 nanomole, right? And the product efficiency is about 41%. But still, this is the first case where I use only a single component system on that. So we also did some organic materials for this. Do I still have time? 1 minute? Oh, 5 minutes, okay. Right. So I think it's enough. So we also tried some organic materials. I'm sure you know about indolin, you guys knows about this better than me. Indolin groups, this is actually a commercially available dyes. It's available on the market, so I used that, I bought it. And I deposited it in the titanium, and we can see this is the data of the lambda max and the extinction coefficient, which is really high. So these two organic materials have also been applied in dye-sensitized solar cells. And we were interested in applying these materials in the water splitting project. First of all, I'd like to show you the cyclic voltometry in solution. We can see there are 3 redox waves, which was assigned to the formation of D+, D2+, and D3+, and this is the same as in the other organic material. Right. What happened when we deposit that and we did the cyclic voltometry on the materials? We can see this is only the titanium, and we can see the water oxidation starts at very high potential. As soon as we deposit the dye onto the titanium nanoparticle, the water oxidation actually only requires 0.6 volts, which is really low, right? So it is a very good indication for us. Right, the linear sweep voltometry also shows that under on and off illumination, it gives us a very reasonably high photocurrent density, above 0.1 milliampere per centimeter squared, between -0.2 and 0 fold applied potential. So this is a good indication for us as well. Right, so the photocurrents, this is, I should tell you, this is actually the first case where we apply organic dyes for water oxidation. No one has reported it before, so this is a very clear indication of the excellence of this material. Right, the D102, D358, it gives about 410 nanomole of hydrogen. For D102 over 1,500 seconds, and we can see here there's a good stability of the 358. It gives about the same moles of hydrogen. And remember that this is actually the control potential at 0 volt, which means that we do not apply any energy onto it. Unlike the other method, which applies more than 0, maybe 0.2, 1 or something like that, but I did apply only zeros, which means nothing is applied to that. Right, so that's a good indication. We confirmed hydrogen, everything is confirmed, but again, this is the problem. We could not see the oxygen. And we start thinking why oxygen is not produced, right? Again, hydrogen peroxide is always the culprit, is always the one that is being pointed at. So hydrogen peroxide is the possible alternative route for the reaction, and we followed that up using the very simple method, using iron 2+, the reaction with hydrogen peroxide, it gives the iron 3+ with the hydroxide anion, right? And we can follow this process using spectral photometry analysis, using the absorbance between about 300 or so. You can see here there's increasing amount of hydrogen peroxide. It gives increasing absorbance of the one in the 200 nanometer region, and you can also see the stated curve there. And this is the evidence of the formation of H2O2, because we see there's a difference between the one that is treated after the photoelectrochemistry and before the photoelectrochemistry, so which means that there is actually hydrogen peroxide there. And we confirm it as well with the fluorescence method using coumarin and umbelliferon. That coumarin can react with the hydroxyl radical. Hydroxyl radical is produced from the degradation of the hydrogen peroxide. As soon as we get the hydroxyl radical, that reacts with coumarin from umbelliferon, which actually gives high fluorescence at about 450. Right. So we confirmed that hydrogen peroxide is formed, and this is the data where we can see the amount of hydrogen produced, the Faraday efficiency based on the hydrogen is about 43%, and we can also see the TON or turnover number actually from the experiments. Okay, so this is the first example that I have given you, the fact that RAN-BP D358, D102 actually can drive the photo-induced photo-oxidation at 0 volt AgADCl, which provides evidence for the first time the biofunctionality of these dyes when anchored to the titanium nanoparticle. I guess when I show this picture, I don't have to give you a lot of conclusion, because you will understand that nanocomplexes can be applied into different fields, including materials, medicine, and energy. So at the end of the talk, I'd like to acknowledge these people. These are the advisors, the mentors, the collaborators. Professor Iji Kobo from Tokyo Metropolitan University, and Kazuyuki Ishii. I was working with him in University of Tokyo last time. And also Professor Leon Spiccia from Monash University, Professor Richard Kin from James Cook University, Australia. The group in Tokyo Metropolitan University, this is the large group led by Professor Kubo. Indra Purnama is Indonesian. He's doing PhD in my laboratory. He's doing mainly on the metal complexes within metal complexes. Opta, she is doing more into organic materials. And Yuta, she is Japanese actually, from the name and from the look. Right, he's doing organic as well as semi-complexes. These are the laboratory. The money comes from JSPS, Japan, Tokyo Metropolitan University. I'd like to acknowledge them as well. Australian government, Australian Research Council is the one that funded some of the research of my past time. And if you want to go to Japan, Japan is a very beautiful country. This is the photograph that is taken during the Easter period, during April, where the sakura is blooming. So you can visit there about from March to April. This is the picture taken around the campus of the Tokyo Metropolitan University. Terima kasih. Assalamualaikum.
And now we direct go to the second presentation, where we presented water Dr. Voltometry, which title is Electrochemical Sensor 4 to 5 6 3 through following based on poly melanin graphene oxide modified electrode. Please, Voltometry.
Thank you for your introduction. Good morning, everyone. So, I'm Voltometry from Peristaltic University. We are from Trace Analysis and Biosensor Research Center. First of all, I would like to thank all of committee and especially Dr. Amin to invite us here. This is the first time to me for here, but actually 3 times in Indonesia. Okay, so first of all, I would like to introduce a little bit about our university. We are from Peristaltic University. Actually, we have 5 campuses, which is Surat Thani campus, Phuket, Trang, and Pattani and Hat Yai campus. We are from the big one, from the Hat Yai campus. So for the detail, Dr. Apon will present you some detail about our university and our chat RC in the invited speaker. So let's come to my talk for today. Actually, my background is analytical chemistry, and then I'm focused on electroanalysis and biosensor. So today I would like to present some of our work on the electrochemical technique for detect 246 nitrotoluene or TNT based on graphene. Okay, I think everyone knows this is a molecular of TNT, and then TNT they are used for military, mining, and terrorist. But actually, and also for the industry, they use for dry industry and some photography. All right, and then actually TNT is have classified to gassy and carcinogen. And this picture, this slide show if human, plant, and animal exposed to TNT, then you get something like that. And then nowadays, US EPA have said the maximum of contamination of TNT is around 90 milligram per kilogram for residential soil and 79 milligram per kilogram on industrial soil. On the other hand, we can use the electrochemical detector TNT to identify the type of explosive that some people use. Like we got in Thailand, we got a lot of bombing, and then we found that some is come from the TNT. So we can use this information. This information could help the naval choosers for who create the device or where it may have come from. That's why we need to develop electrochemical detection to detect TNT. Actually, they use chromatography technique, which is gas chromatography and high-performance liquid chromatography. Both of them is really good, but they have some limitation like expensive, long-term analysis and need expertise. So that's why we need to develop some cheaper equipment. And the first, I would like to introduce something about it. We also developed the color test to detect TNT on field. Just the chemical test, we can use acrylamide mixed with acetone and water, and then after that mix with TNT, and then we try to develop the standard color to compare how much of the concentration of TNT. Like we can detect by naked eye or spectrophotometry. But in this case, for spectrophotometry, the problem is the limitation of, the concentration of it can detect is allowed ppm. But in the case of ultra-trace analysis, we cannot. That's why we move to this is for example to how to detect TNT on mobile phone, on the can or something. And then we can detect by naked eye and spectrophotometry. And then we move to electrochemical technique to can detect in the ultra-trace level. Because especially the absorptive spin one chemistry, because the electrochemistry is really easy to use, portable. The I think the size is smaller than your phone. Actually, electrochemical electrochemical equipment, they have many models. If you have no money, so you just use the smaller one. Yeah, the price not so expensive. Like in Thailand, we bought 115,000 baht. It's quite cheap. And then this equipment is really high sensitivity and rapid result, and we can use really low the sample. Nowadays, a lot of people try to use nanoparticle to enhance signal, to enhance everything, and then they have many reports that use mesoporous carbon nanotubes and graphene. Among all these, graphene is quite interesting because it high conductivity, large surface area, and excellent electron transfer. In our case, actually, they have some report that use graphene modified gaseous carbon electrode to detect TNT, but they can detect only 1 ppm. And then we think, okay, in this case, it cannot detect in the level of contact trace TNT. That's why we think it would be important to find a new fabrication strategy to improve the absorption and electrochemical reduction performance of TNT by enhancing the detection limit. And then we try to create the new one for, we call amino functional graphene oxide with polymelamine or PM. We use that one to absorbent, and then use for working electrode because the molecule of the melamine, they have the 6 ring, and then it can, this is molecule of the TNT. TNT can adsorb on electrode surface by pi interaction and also by the hydrogen bond between the nitro group and then amino group of the melamine. That's why we think we create the new strategy for modified electron. This is our objective. And then in our work, we try to fabricate polymelamine graphene oxide on calcium carbon electrode. First, we modify graphene oxide by electron deposition, and then prepare and fabricate polymelamine on the electrode surface by electropolymerization. And then, first of all, we need to improve our system. Is it good or bad? What is the electrochemical property of the electrode surface? Let's see, in this slide, this is we try to prove is that our modified electrode is good or bad by using electrochemical technique. We call Cyclic Voltometry. And then you can see, in case of calcium carbon electrode, this is the bare electrode. After we add, after 0.1 milligram of TNT1 addition on the solution, you can see the redox flow. In this case, we use folic cyanide as a redox flow, and both redox didn't change. That means TNT cannot adsorb on the gaseous carbon electrode. And then next, this is we modify just only graphene oxide on top of the gaseous carbon electrode. You can see after modify with graphene oxide, the redox peak increase. That means surface area increase. And after that, when we add 0.1 ppm of TNT, the redox peak decrease. That means the molecule of the TNT can adsorb on the electrode surface by pi and hydrogen bond. And then for the last one that we propose, you see, after this is include melamine. After 0.1 of TNT addition, and then you can see the redox peak also decrease too much. In this case, we can conclude that our modified electrode, TNT can adsorb on electrode surface by pi and hydrogen bond, and then we try to use another system we call adsorptive stepping voltometry, and which is the two steps, the pre-concentration step and stepping step, and we get very good signal. You can see we got 3 peak of TNT because TNT they have 3 nitro group, and then they will the first reduction peak of nitro group become to amino group in the first peak at the minus 0.5. The second one is minus minus 0.59, and the last one here. And you can see when we compare between calcium carbon electrode, graphene oxide, melamine graphene oxide, we found that our proposed method is really good signal. That means we can enhance the signal for detect TNT. And when we compare, this is for example of the Cyclic quantum program. You can see when we compare the sensitivity between each electrode, our proposed method, the sensitivity higher than 3 times when compared with graphene oxide, and more than 11 times when we compare with calcium carbon electrode. And in this case, for all the results, we can conclude that our proposed method, is provide excellent absorption and excellent electrochemical reduction for TNT. And also, we need to optimize, a lot of things that we need to optimize because we are analytical chemistry, and we need to optimize a lot of parameters such as amount of graphene, the concentration of melamine, and also the deposition times of melamine. And also, we need to optimize the concentration potential and concentration time for the electrochemical detection. And then this is our criteria. We select the high sensitivity and the short analysis time. And this is the table that we are conclude our optimum condition here. And then after we got the optimum condition, we found that we got 2 linear range because this is the first linear range and second linear range. The first linear range is because of it is very low concentration of TNT, and then TNT absorbs on electrode surface like a monolayer. That's why we get the first one that very high sensitivity. And the second one is the sensitivity too low because it's too much. The concentration of TNT can absorb on electrode surface like a multi-layer. That's why the sensitivity is decreased. And then we found that we got the LDLQ is the range of ppb. And also we need to, when we develop the new modified electrode, we need to check the repeatability. In this case, we prepare 1 electrode and we do 6 sets of experiments. We found that the percentage is not much lower than 5.8%. And also we perform by 6 electrodes and then compare different concentration of TNT, and we found that the percentage is lower than 9.4%. In this case, we can conclude that our electrode is very good repeativity because it's lower than the rule from AOAC guideline. And then we need to check the specificity. You can see when we use TNT at the same concentration, we got the signal from TNT, but for the other, like RDX, C4, dynamite, urea, nitrate, lenatite, we cannot get the signal. So we can say that our system is really good specificity, and also the metric effect we also test. And then we also try to do in the real thing. This is we sampling the TNT that already involved in soil, and then when we compare with the standard method that we use, EDC, when we compare, you can see, for sample 1 and 2, the concentration that we get is the same. It's very good agreement together. And then also, we try to prove our system by using the perceived recovery, and we found that perceived recovery is very lovely, very good. And also, we need to compare with other methods that modify electrode to detect TNT. This is the hour. And you can see the detection time lower than, and now we got the wireless linear range and the very low detection limit when compared with another modified electrode. In this work, we can conclude that our system provide really low detection limit, short analysis time, good repeatability and selectivity. And also, it can apply to the soil sample. And also, we get really good recovery. And this is possible to apply our proposed modified electrode to detect TNT on the forensic sample or on the environmental. And you can get more information from electrochemical data. This is very, very good journal. And also, I would like to introduce something about our work in Thailand, just briefly and quickly. This is also, I still have time? Okay, thank you. And this is we also try to develop nitride. We got this project from the police, and then you see we developed the test kit to detect nitride. Not only for color test, we also developed for electrochemical technique to detect nitride. Also, we use single nanoparticle and mix together on the modified electrode, and then we produce wholesale, and we get very good signal. Also, we can see, and it's very fast rate. What you can see, 1 hour we can detect 180 samples. It's really fast because the flow rate, you can see the flow rate that we use 2 milliliter per minute. And also, this is for example, because I'm from the forensic side also, we have the Master of Science, and we need to create electrochemical technique to detect everything for the forensic side. This is psilocybin, you know, psilocybin actually the doctor use for if they want to operate the dog or the cat. The doctor will keep that one. But you know, in Thailand, they have some bad guy to use this drug to women for drinking, and then when women cannot breathe, something like that, and the women do some bad to the woman. Yeah, like the news in Thailand, it's too bad because this chemical is not smell, just like the water. You know, when women take nothing, and then we can say that we are the first time to develop electrochemical method to detect psilocybin, and we get a really good signal, and you can see, and also we need to modify with graphene oxide, something like that, and also alpha solam. I think everyone knows alpha solam. You know, some girl use alpha solam put on her body. You know, when the guy do something, and then the guy, and the woman will give some mobile phone, some money, something from the guy, something like that. And also, we have a lot of news about that, and that's why we try to develop very quick method to detect this is alpha solam or not, something like that. And also, we also develop using just simple method, and we get very good signal also, and the potential minus 1 point something, very good. And also alpha solam. Yeah. And this is the drug from sex. Yeah, it's too bad also. And we also developed that one to detect UV. You know, we got very good signal. All of them is still writing the manuscript. If you want to have a read, I think maybe next 2 or 3 months you will get from the website. And also we develop electrochemical to detect zinc in human similar fluid. You see, because actually if you detect from some protein, it takes a long time, the protein will degrade. So we can detect zinc. You know, we just use the simple method to detect zinc also. And also the chlorine sensor, you know, we use electrochlorine to detect chlorine. And then now we develop like the prototype to detect chlorine, and also like a watch, you know. I make this one and then make my daughter. When my daughter go to swimming pool, and he just use the watch and the swimming, if the color, you know, something like that, that means the chlorine in swimming pool is more than the limitation. If the white one, that means my daughter is really helpful. No problem about the chlorine in swimming pool. And also we just writing the patent about that. I hope that in Thailand it may be some company to license our work. Oh, sorry. And also, yeah, this is hydroquinone for the whitening cream, you know. And also we develop formalin. This one we use palladium nanoparticle modified on with caffeine also to detect formalin in seafoods. And also hydrogen peroxide, we use calcium carbon spear and we synthesis simple nanoparticle on the calcium carbon spear also. And this work we use palladium to detect glucose also. And this is actually this one we got the copper line silicon wafer from Professor Taiwan University, and then they said that it should be made for sale asked me to make for sale for him to make the sensor for hydrogen peroxide, and then we can got the signal, and then we send this photo to him. And also, for the last one, I would like to talk to you is that we also develop some test kit to help the agricultural. We can call that this is our innovation that we make from chemical classroom, because in this kit, every step that we use the normal knowledge from the chemical classroom to make that one. And also we have 3 patents in Thailand. Nowadays, they have 2 companies license that one to sell in the market. And this is all of Thailand use that one also. And I would like to show like an example that we are the scientists, we need to do something for the social. And also I am the one in the Thailand that make the innovation for the social also. This is we go to the outside and then transfer technology to the farmer. And you can see when we compare between zinc deficiency and no and zinc enough, you see it's quite different. Yeah. This is for example, you can see. Yeah, and in this set we got many awards from Thailand and also in the overseas. Okay, and we are not actors, but we have if you have good work, so you can go to the television or the news or something. Okay, last one. You should have inspiration, because I think maybe some student or some young lecturer, it should have inspiration to give to put yourself go to do the good thing, And also all of them, I would like to thank all of this, because all this is my university, and all of this is our agency. If not, I cannot do anything, And also, this is our group, we are very big group, and this is my advisor here, and my advisor. Also, I would like to thank my advisor, Associate Professor Dr. Manotharamangun, and Associate Professor Phunpit Thanadana. Both of them give me a lot of opportunity and give a lot of power to me, and then to do something with us, Okay, I think, sorry for the quick talk because the time limitation. I think if all of you have some question or something, maybe we can talk later. Okay, thank you very much.
And that speaker will be presented by Roy Andreas, PhD. And the title is Trace Metal as an Enduring Parameters, Potential Between and Presence of Processes Now and in the Past of the Years. Please.
Okay, Bismillah. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to say thank you very much for the committee of this conference. Already give me a great opportunity to share my research, what I ever done and still doing now. My topic will be a little bit different maybe with others speaker. Other speaker, they are talking about how to develop a new material. Another speaker talking about how to develop the method to analyze some. For me, maybe how to use chemical compound to understand the phenomena in the earth, or especially in the ocean. Maybe we're still talking about the chemical compound, but in my topic, I would like to share about how to use some chemical compound to trace or to understand the phenomena in the earth, especially in the ocean. Just let me know that some people told me that if you want to peaceful in your life, you have to closer with the nature. How to close the nature? So you have to understand about the nature. So that's why I did this kind of research. So I hope that I can be kind of peaceful in my life. Okay, the title of my presentation today is Trace Metal as Environmental Parameters, Potential Nutrients, Trace of the Process Now in the Past of the Ocean. Later we'll be talking about a little bit history about the Earth. Okay, this is my name, Roy Andreas, and then my affiliation is Department of Chemistry, Jenderal Sudirman University, and also I active in the Center of Maritime Bioscience Studies, Jenderal Sudirman University. Okay, this is just this figure. We can see together that in this figure there is biogeochemical cycle of the trace metal, or maybe some people call it with the heavy metals, something like that. Maybe I will not explain one by one, but you can show that actually all the material in the world, including trace metal, will be make a cycle. Yes. For example, from this figure you can find that the source of the trace metal can come from the nature, come from the human activity, go to the ocean or maybe water system, and then come back again to the land by so many processes inside of them. More deeply about this, I would like to introduce some important biogeochemical process in the ocean. I took this one from the Moore et al. 2003. The paper is Science Journal. There is so many trace metal very important for the biogeochemical process in the ocean. Like this. Iron and manganese very important for the carbon fixation, and so many trace metal. Maybe the previous time, some researchers, including me, just thinking if we are talking about the trace metal, talking about the heavy metal, we only thinking about the pollution problem or something like that. But actually, trace metal can be useful also for other things that finally we can understand the phenomena in the earth, or especially in the ocean. Next. Okay. More deeply about this, so I bring you to one of the benefit of trace metal to see how the trace metal can influence the marine plankton. Just like this. For the limited trace metal concentration, so the trace metal can be very usable for a macronutrient for the marine plankton, just like this figure. Okay, next. Again, I took one data from the nature. Ambras 2009 do an experiment in the equatorial of Pacific. We found that there is very different condition, even the location is close enough each other. First location in this area, there is no ion fertilization, and the effect is the population of the organism in that place is very low. Compared with another place in this area, in the B area, there is ion fertilization. He found that the population is huge population at the time. In the same time, very close location, but the ion fertilization can influence, very big influence for this area. Okay, next. Okay. So to explain about this, I do some experiment together with some professor. For sampling, I took around 185 days in the ocean. This is the times, and then this is the observation that I ever did at the time, and this is the ship that I used at the time to collect some samples, sediment sample, and then water sample in the ocean. This is how to get This is the equipment how to get the sample for the sediment sample. This is grab sediment sample. So this is multiple core. This is the piston core sample. This is how to get the water sample. This is clean water. This is large volume seawater sample. This is useful to collect so many water, which has maybe radiation, some nuclear plant, something like that. And then this is another document how to collect the sample. Sample area. I took one sample for area. Okay. I took one location in the East China Sea. In this area, I took around 9 stations for sediment sample and water sample. By using this seed and this equipment, and this is how to treat the sample, sediment sample. Actually, the phenomena in that area, just like this figure, the trace metal come from the land, go to the ocean by several ways. First is by atmospheric input, and second one by the river input. And the trace metal in the ocean, they make interaction with some compound, organic or inorganic compound. And finally, some of the trace metal will be deposited via sediment in the sea floor. From this phenomena, so I have at least 3 scientific questions. What is the source? Second one, how significant this trace metal will be a macronutrients to support plankton growth? And the third question is how the potential risk, because some of Japan government worry about this because the source, so many sources come from the China, something like that. So, and then continue. Now, what I did to make okay. This is the method that I use to how to separate between one trace metal to other trace metal in the same sample sediment. This one. Maybe you can see the figure like this, just like this. So that means I can separate at least to be 4 phases and 4 characteristics. Okay, continue. We call that this BCR sequential extraction method. This is what I did in the lab, how to separate between one trace metal characteristic and others, just like this. Continue. Okay, continue. And this is some of the equipment and instrumental that I use. So the time, yeah, continue. And how about the result? Okay. Before go to the what's the function of trace metal via macronutrients. So in the ocean, we have to characterize the location at least by using the hydrology setting, just like this. We using the TS diagram. TS means temperature, salinity, and dissolved oxygen to characterize the location of sampling location in the ocean, characterized by the hydraulic TSDO diagram. From this characteristic and use some reference, this is reference, some paper. So I got that actually even this small area, but the characteristic was different. I divided into 3 groups, at least the northern East China Sea, the middle East China Sea, and the southern East China Sea. And each group have their own characteristic. Okay, continue. I took some maybe sample because the moderator told me that I just have 15 minutes to present all. 15 minutes. So that's why I will do very fast. And then this is only one sample of manganese. By using this BCR sequential method, we found that there is 4 phases, and this is the explanation what is it. Manganese station or big version in the oxide phase, so that means it's from the hydrate manganese oxide and oxide phase. station, especially station 1, 2, and 3, in the southern of the East China Sea, we found that the hydrothermal plumb in this area influence. Hydrothermal plumb is come from the volcano, submarine volcano. Okay, continue. This is also the zinc. I found that it is very similar with manganese. I'll continue. And then this is the cobalt and iron. Specific for the iron and cobalt, we found that the mainly found in the residual phase. So that means the iron and cobalt in this area almost come from the lithogenetic source, or maybe the nature. Okay. One instrument to make correlation between the trace metal and some other parameters, I use the person for relative coefficient to see the correlation. So from this data, I found that oxide and organic phase have a good correlation with TOC and ACO2. So that means from some reference we found that hydrothermal and biogenic source very influence in that area. Okay, and I'm using also some reference to see how about the relation from three reference, at least three reference. If I make group, this is the group, the lithogenetic source, that means from the nature. This is from the hydrothermal, from the submarine volcano, and then this is the biogenic from the phytoplankton or something like that. And I found that group 3 in this area, because the ratio between the iron and manganese in this area is between hydrothermal and lithogenetic. So that means in this area influenced by hydrothermal and lithogenetic. Different with other group 1 and group 2, we found that in this area is very close with the lithogenetic only. Okay, continue. And then when I saw more deeply about the group 1 and group 3, group 1 and group 2, so I found that the location is between biogenic and lithogenic if I'm using zinc and cobalt, because zinc and cobalt is parameter for the biogenic source in the ocean. So I found this, and lithogenic still more influence compared with the biogenic. Okay. This is, I tried to calculate also how about the potential remineralization of the trace metal. I found also from this. So 15 minutes is including this problem or not? Okay, from this calculation, we found also the atmospheric input is, especially in the group 3, in the southern of East China Sea, is lower compared with the river input, or maybe from the volcano or submarine volcano input. Okay. From this situation, I make kind of the conclusion, small conclusion, that just like this. So trace metal from the land, by the river or by the atmospheric input, they have correlation, they have interaction with others, and then finally like this and like this. Okay, you can see from the figure here. Okay, continue. And the implication of this situation. So in the previous time, so many people told us that the northwestern Pacific Ocean, the trace metal for macronutrient in this area is only supported by atmospheric input. But in this case, I thought in one of my papers said that the northwestern Pacific not only atmospheric input, but also have a potential influence, support by the sediment from the submarine volcano. Okay, continue. This is maybe some of us already familiar with this one, so I want to remind again how to use the same data also to see the environmental parameter, the pollution parameter. Just like the contamination factor, we found that cadmium high contamination factor, so that means risk is very high. Let's continue. And also by using risk assessment code, you can see that also some of this metal is very high risk and some is still low. Let's continue. Yeah, continue. Continue. Yes. For how to trace the present and the past ocean by the trace metal also. We have very simple method how to trace, how to see the condition in the ocean in the past and now and predict the future. So we are using the ratio between magnesium and calcium. By using this one, we can understand that in that place, the sediment condition or maybe the environmental condition at the time, just like what? Okay, maybe from this slide you can see. Continue. This is only simple explanation also that in the sediment we found that foraminifera, this is the one of the species and very long. We have very long life, and we can using foraminifera to see the history of the ocean. The simple thing is, the characteristic is the foraminifera in the cold water, the very small amount of magnesium will be absorbed to the foraminifera, but in the warm water, so many magnesium will be absorbed by foraminifera. So by using this one, we make kind of calculation, and then we found that we can understand. For example, first step is sediment. We took sediment and then we predict the age by the lead isotope. For example, 10,000 years ago, something like that. And then what happened in the 10,000 years ago? So by using ratio between magnesium and calcium, we can find that temperature at the time 100,000 years ago, how about the temperature, and then also, so at the time we can predict also what kind of population, what kind of the organism who can living in that time. Okay, for this research, so many professors helped me, so many professors give me suggestion, many from the School of Science and Engineering, University of Taiwan, Japan, and also from the Atmosphere and Ocean Research Institute, the University of Tokyo, Japan, and also Japan Agency for Marine Science and Technology, JAMSTEC. Okay. Thank you very much for your kind attention.
And now the time for question time, discussion time, and please for all that have a question or comment, and also please mention which speaker related for your question. And in the first time, we please make a question. For the 3 questions, please. Yes, okay. Please make a question and 2. Yes. Okay.
Actually, very interesting presentation. I have 2 inquiries. The first one is usually one of your slides, one of your early slides. Is it a stable radical or short life? Because it this situation can be used for electron spin resonance, say antioxidant activity and similar. That's part one. The part two is also is you showed a spacer, C5 spacer. What is the role if you, and then sometime you will engage the spacer to 8, I think, or the spacer between the two aromatic groups. Can you explain the role of the effect of the spacer? Thank you.
Please, you can directly to answer.
Thank you, Professor Hassan. The radical, the first one, isn't it? The cobalt with the semiquinone and, is that the one? Right. Okay, that radical is stable, very stable, that's right. The stability comes from the interaction between that radical ligand with the cobalt center, actually. So we can move from cobalt-3 third butyl catechol to cobalt-2 semiquinone very easily. So that's why it's bistable. The reason being is that it has a bulky third butyl group, which actually gives the better stability of that radical. Otherwise, if you use only catechol, it's not stable without any third butyl group there. So that's part of the reasons why. Right. And the second one, the spacer actually plays quite an important role in the activity of the anti-cancer activity of those complexes. I think it's partly because of the, maybe, I think those who works in the biochemistry field, I think understands the lipophilicity, I'm not sure about that, the ratio between, see there's a charge and there's a lipophilicity as well. So it can play, for example, if we have large charge, 4+ charge with little lipophilicity, then it's not going to be entering the cell.
Yeah, in other words, you will engage.
That's right. When we make it longer, that would give more lipophilic, which potentially be able to enter the cell because of the the ion. I don't know. Lipophilic channel. I'm not sure. I'm not a biochemist, but somebody can answer that. But that's the reason why. And it actually relates to the activity of the complexes, which actually I showed you that last time. That the one that has 16 chain length is the best one for that. Yeah.
Okay, the next one, please. Make a question or comment.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, Associate Professor Yan. My name is Rosie Zamahandina and I'm from the Islamic University of Indonesia. And I would like to give one question because I'm very interested with catalysts, heterogeneous catalysts. So, have you ever do the reusability of that catalyst used for water splitting to get hydrogen? And then how many times? Because I'm very interested about that. Thank you.
Did you mean the reversibility in the cyclic voltometry and things like that? The catalyst itself, the stability.
Yeah.
Right. Okay. Most of the ruthenium complex are stable. Most of the ruthenium complex. That's why people are actually focusing on ruthenium complexes because of the, high inertness. If we compare the complexes, cobalt, manganese, iron, and things like that, cobalt, manganese, iron are really labile, but the ruthenium complex is very stable. It's highly inert. That's why it's been used as a water oxidation catalyst. But having said that, it's also facing, I've done the homogeneous catalysis using that metal complex. It only survives up to maximum 4 hours. So that's the limitation of that the metal complex on that. It's until now, there is no single ruthenium catalyst that survives forever. Like maybe, I don't know, maximum, I don't know, 6 hours or maybe even 1 day, if we use the homogeneous catalysis, right? But in heterogeneous catalysis, it might be a different story, because we attach the catalyst into the nanoparticle, right? That would give a longer stability in theory, but again, because we use the light energy to it, so that would give, you know, photo instability to that one. So that's how we develop something that has a longer alkyl chain, which would give a longer stability on the surface of the titanium nanoparticle. So that's a story of stability of the nanocomplex. Pardon? It's not practical. It's not practical. If we regenerate it, it's not going to be regenerated that easily, right? So that's the limitation, the current limitation. If you see the efficiency of that particular material, there is no single material that has exceeded 1%. Unfortunately, now even the Daniel Nocera in Harvard, or somebody somewhere in the high, you know, ranked university in America, there's none. It's still a long way to make it practical. Yeah. But we have to go there. That's it.
Okay. Have the question. One question more, please.
Nobody want to? Yes. Thank you very much for Dr. Yan. It's sorry. Okay. Actually, even you say that this is good for change, good for everything, for any purpose. So my question is, how about the cost? Yes. Because maybe you can easy or maybe very cheap to make that chemical compound. But how about to apply this material compound, this material to split for example the water? How about the quantities will be very costly or what?
The answer to that question is not easy, because well, if we think of the cost of the ruthenium metal breakthrough, that is really costly. I'll tell you what, the ruthenium precursor, which is ruthenium chloride, it cost me about, I don't know, 5 gram cost me about, I don't know, 20,000 yen or something? Yen?
2.5 million rupiah.
2.5 million, that's for 1 gram. 1 gram, right. So that's the precursor only. And we need to go from that to make the metal complexes and to assemble it in the material and things like that. It's really, really costly. That is why people in Harvard, they use cobalt oxide, right, for water splitting. For that reason, they don't want to use ruthenium for the material, but again, at the same time, they have to apply potential to it, which means adding energy to produce energy, right? Which is not really practical. But in my case, in our laboratory, we are thinking that it's okay to use that sort of material which is costly, but we do not use much energy to produce energy. As I told you in my slides, that I only use 0 applied potential and only use sunlight energy for it to work. So that's the sort of compensation between the cost. Yes, we do the costly one, but then we also go for another sort of purpose. Imagine if you want to sell something to the market, you need to sell especially Japanese, the Japanese products, they're really good in, selling products and say, oh, this is our advantage and that's your advantage. So we think that this is the best one, the best technology we have now. So that's pretty much to explain the question. Thank you.
And now, because the time is limited, so if you still have a question, you can go to directly to the speaker in the coffee break or another time. And for all nice presentation, please to participant give applause to our speaker. Thank you.
Ladies and gentlemen, this is the time for handovering a token of appreciation to invited speakers. So please, to Mr. Swandri to handovering the token of appreciation for Mr. Yan Mulyana.
And the second token of appreciations, we'd like to invite Mr. Amin Fatoni, PhD, to hand over token of appreciations for Assistant Professors Warapan Limbut from Thailand.
And we would like to invite Mrs. Dwi Udiani as the head of Department Chemistry from University of Diponegoro to give the token of appreciation for Mr. Roy Andreas.
And we'd like to call the speakers to have photo session first, and also for the VIP guest and Professor Dr. Hassan, and also to Mrs. Dwi to have photo session first.